Okay, so let's begin with 4.9 types of friction. Now, there are two types of friction. There is one called static friction, which is the first one we're going to talk about. Now, when an object is in contact with a surface, there's always a force acting on it. When an object moves or attempts to, there's a component of force parallel to the surface known as friction. This can also be called static friction. For example, picture a tire. Without friction, car tires wouldn't provide the traction needed to move the car. If there is no friction, the tire would just slide and the car wouldn't be able to move. Now, the first type of friction, static friction. Imagine a block that's at rest. If you don't attempt to move, there will be no force acting on it. But when the force is applied to it by a rope or by someone pulling or pushing, then the object will begin to move. Now, if the force is small, then the object will not move, and that means that your static friction is its maximum. Now, your static friction will always be opposite to your force. So, if your force is going from the left, your static friction will be pushing from the right. Because they will always cancel out and your object will not move, static friction will always be equal to the force applied. Now, the maximum static frictional force is the force big enough, the maximum force that the block moves just before it breaks away from the surface. Now, the coefficient of static friction is known as the proportion between the maximum static frictional force and the magnitude of the normal force. These two will always be proportional. However, this coefficient also depends on the type of surface that the tire or the object is sitting on. So these are a couple of examples. Now, the second type of friction is the kinetic friction. Let's picture a block again. As the block slides, the static friction turns into kinetic friction. You break from static once it starts to move. Now, when you push an object, it's easier to keep it in motion than when it is to get it to start to be in motion. That's because you use less force. Now, according to this, the magnitude of the kinetic frictional force is given by force of kinetic equals coefficient of kinetic friction times normal force. So you can see here how the normal force is always also proportional to the kinetic friction. Now, let's look at some concepts. Suppose that the coefficients of static and kinetic friction have values that are that the coefficient of static friction is 1.4 times the coefficient of kinetic friction. Which of the following statements is true? Now let's look at A. The magnitude of the static frictional force is always 1.4 times the magnitude of the kinetic frictional force. Now this could be it. So let's leave it and go to the end. Look at B. The magnitude of the kinetic frictional force is always 1.4 times the magnitude of the static frictional force. Now, just by looking at the equation, you can see that the 1.4 is on the side of the kinetic frictional force. So, if anything, the 1.4 will be applied to the kinetic frictional force, not to the static frictional force. So that cannot be it. Now, let's look at C. The magnitude of the maximum static frictional force is 1.4 times the magnitude of the kinetic frictional force. Now, this is the answer because it has to be the maximum static frictional force because that's the moment where it starts to break away. So it has to have already broken away for it to be 1.4 times larger than the static frictional force. Now let's look at another concept. A person has a choice of either pushing or pulling a sled at constant velocity, as the drawing illustrates. Friction is present. If the angle theta is the same in both cases, does it require less force to push or to pull the sled? Now remember how the angle affects. Now, if this would be that it requires less force to pull because the upward component of the pulling force, meaning it reduces the normal force. When you lift the crate, it'll lift it and cause a less friction, and the sled will move easier. However, when you push a sled, you're pushing down on it, so you're creating more friction, and the normal force will be pushing up at a greater level, and therefore it will cause to be harder to push the sled. Now, the last one. A box rests on the floor of an elevator. Because of static friction, a force is required to start a box sliding across the floor when the elevator is stationary, accelerating upward, and accelerating downward. Rank the forces required in these three situations in ascending order. That is smallest first. Now this one we can look at the previous example and use the same thought of mine. Now, if a force is stationary, that means that nothing is there's no force pulling it in any kind of way, so it's sort of equal. So if the elevator is accelerating upward, then that means that as you go up, there's a greater force pushing you down, so the static friction will be the greatest. So we know that B will be lost. Now if an elevator is accelerating downward, that means that a force is pushing you up, and when it pushes you up, it sort of lifts you up and your friction will be reduced. So that means that it has to go before B, and it has to be first. So just knowing that, we know that the answer is C, A, B.